Yeah, I got the pictures of you, so I can recognize them. I mean, it will take me a while to learn all the names. All right, so how's it going, I mean, with the other courses? At the moment, you have 2 courses have started, right?
Yes.
The mathematical methods and RQM, right? Okay, so what I will be doing is the group theory. So on. Okay, so Lie groups. Lie groups, and actually mostly Lie algebras. And in the group part, I will be discussing very little, mostly Lie algebras. Okay. Now this is actually, I mean, very important, particularly for your second semester course. Not the second semester, also the first semester course, but particularly second semester course, because as you know, probably you have heard about it, that the standard model of particle physics is based crucially on symmetries. You know, there are symmetries, a lot of internal symmetries. Certain symmetries you already know, right? In a vacuum, you have a rotational symmetry, right, or translational symmetry, right? These are space-time symmetries. You have seen in the relativistic quantum mechanics, I don't know to what extent you have reached there in the course, but there's also the generalization of the translational and rotational symmetry to Lorentz-Poincare symmetries. So these are all space-time symmetries. But apart from that, there are also some things called internal symmetries, okay, which act on some hidden degrees of freedom of particles or fields and so on. So those are the standard model is based on certain internal symmetries. Apart from the usual, Poincare symmetries will always be there. But apart from that, there are also internal symmetries which go under the name of SU2, I mean U1 times SU2 times SU3. Okay, we will discuss all these things in the coming lectures. But I just wanted to motivate why I want to study this subject, and this will be crucial. The entire standard model of particle physics is based on this internal symmetry. Okay, these are actually gauge symmetries. Again, I will discuss that later. Gauge symmetries. So, in fact, I mean, most of the course, although this course will discuss in more general Lie algebras, okay, but I will be focusing particularly on SU2 and SU3. So something like almost half of the course will be devoted, not half, maybe a little less, 2/5 of the course will be devoted to discussing SU2 in detail. Okay, and I expect that each one of you should be completely comfortable with SU2 by the end. It's very easy. You already know quite a bit of it, probably without using the name SU2. Okay, but I think you have already used that in quantum mechanics. So the SU2, and then SU3, because this is the symmetry behind the strong interactions. Okay, so these two. So this will be this I expect everyone to understand, and then we see SU3. Actually, you will see the way when the course proceeds that if you have understood SU2 very well, then it will be possible to understand everything else. Because basically everything else is understood in terms of SU2. Okay. So this one, and then once you also go through the SU3 discussion, then you see how you can use this information to understand more complicated groups, and then you can generalize it to anything else. So towards the end, I will generalize it. Towards maybe the last 3-4 lectures, I will go beyond, so generalization. But most of the course will be focused on that. In fact, you can generalize and you can completely classify all some algebras called simple algebras. Okay? So there's a complete classification of that. I don't know whether I will reach there, but most probably not. But I will at least give enough kind of tools so that if any of you is interested later to go ahead and try to learn all the group theory, all the Lie algebras, then you'll have enough tools to understand that. All right. So now what I will do first of all, let's look at the abstract definition of. By the way, you have not received the notes yet, but I requested Patricia to send you all by email, the PDF file of the notes. And eventually, I think maybe it may take a few days, you will get also a hard copy because it has to go through the printer's office. So it may take a few days. But at least you will have the PDF. I think by the end of today probably you will have that PDF. Okay. So first of all, let's see what is the group. Okay. So let me just start with the formal definition of the group and then start giving some examples. Okay. So the group is first of all a set of elements. So it's a set of elements. It may be this set may be a finite set, or it may be not finite, infinite set. Infinite could be countable or uncountable. Okay, so there are all possibilities. But at the moment, it is a set of elements, and let me just denote them by G1, G2, etc. Okay, these are there's a notation. Elements of this set will be called G1, G2, G3, etc. Okay, this is one thing. Second, there is a operation. I will denote it by a not. An operation defined such that, say for any two elements, say let me just call them G1 and G2. There is an operation G1 times, let me just think of it as a product, although it's not product in general, but G1 times G2 is again an element of, so I will call this set of elements as G, capital G, is again an element of G. Okay. So you can think of it as, suppose these were just real numbers, okay, and this operation could be just addition. So add to any two real numbers, you'll get a third real number, right? So this is the important point, that there is some operation, an abstractly defined operation, which has been defined, such that for any two pairs, you get a third element. This may be some G3, let's say, which of course belongs to G. Notice that it is not necessary, this does not imply, in general, this does not imply that G2 times G1 is also equal to G3. That may not be. When this happens for every two elements G1 and G2, G1 times G2 is the same as G2 times G1, then that group is a particularly simple group. I mean, it is called abelian group or commuting group. But in general, it need not be. In fact, in all these examples, SU2 and SU3, it will not be the case. Okay? So it will not be commuting. U1 is something which commutes. So U1 is an example where this is true. If G1, G2 is equal to G3, and then G2, G1 is also G3. So the important point to remember is ordering is important. You know, which element you write first and which element you write second, you have to be always careful with that. Huh? Okay. So this is one thing. Third is that with respect to this, so with respect to this operation O, there exists a special element called identity. Okay, which I don't know. Let me see how it will be defined. What notation we use for that? I think it's okay. Here we have used the notation E, and I will denote it by E. Nothing to do with exponential. Okay, just E. So what is the property of this identity? It means that E times G for any G, this G belongs to any arbitrary. So for all G belonging to capital G, of course E belongs to G, right? Because we are saying there is a particular identity, a particular element in G, okay, which I call identity, such that E times G is equal to G times E is equal to G itself. Okay? So that's the reason why it's called identity. Like in the product, for example, when you multiply, 1 is an identity. Okay? So that's one thing. Fourth, that for every G, there exists an inverse, which, let's see, how do we indicate? We just call it G inverse. Huh? This does not necessarily, this is a notation, G inverse, such that G times G inverse is equal to G inverse times G is equal to the identity. And okay, one more property which I forgot to mention here. Let me just write that. And one other property here, already I should mention here, is that this product rule, sometimes you call this operation as a product rule, okay, or sometimes composition, like because it's composing two elements. This product rule is associative. Associative. Okay. So what it means, if I have, say, three elements, G1, G2, and G3 belonging to capital G, okay, then if I first multiply G1 with G2, I first take the composition of G1 and G2, and take the composition then with G3, okay, it's clear, because this suddenly, by this rule, that this operation is defined, so this guy is an element of G, right? G3 is already an element of G, so G3 with times this, okay, is again going to be some element of G, so this certainly belongs to G. But then the important point is associativity. This associativity is saying that it doesn't matter, you could have done first G3 with G1, okay, and then multiply that with G2. So this is what's called associative. Yeah. Okay. So yeah, this is a kind of defining equation. These are these two properties. This property that this property is usually called closure property. That this operation closes within the group. You take two elements. The composition is again an element of the group. It doesn't take you out of it. It's inside them. And then this same operation also satisfies the associativity condition. Okay. This other thing. And then we further require that there should be an identity, and that for every element there must be an inverse. Okay. This is the basic abstract definition of the group. Okay. Now let me just give a few examples to illustrate this, because usually the abstract definitions are kind of difficult to appreciate. Now, can I erase any of these parts? Unfortunately, the blackboard is not so big. Maybe I can just erase this part here. So let me take some examples. First of all, let's consider finite groups. Some examples of finite groups, which means there are only finite number of elements inside this set. So let's take the element, the example. Take 1 and minus 1, the ordinary numbers, 1 minus 1. The product rule is clear, and the operation, this operation O, is just the ordinary multiplication. Okay. Well, it's clear. 1 times 1 is again 1, right? 1 times minus 1 equal to minus 1 times 1 is minus 1, and minus 1 times minus 1 is 1. So you see this operation that we have defined here, which is ordinary multiplication, it closes, right? Because what you get on the right-hand side is again an element of the group. So certainly closure property is satisfied. Associativity is obvious because any multiplication is associative. The usual multiplication that we have is associative. So associativity is immediate. Okay, what about the identity? Well, identity is nothing else but, so I call it E. E is nothing else but 1 here, right? Because you see 1 times 1 is 1. 1 times minus 1 is minus 1. Right? That's the definition, right? E times G for every G is the same as G. Right? So E identity is 1. And what about the inverse? Inverse of 1, inverse of the identity, so 1 inverse is clearly 1, because you see 1 times 1 is 1, right? What about minus 1 inverse? Minus 1 inverse is minus 1, right? So we see the inverse also exists. So this is a group. This group is, by the way, called Z2 group. It's usually in the literature, it's denoted by Z2 group. 2. So let me just continue why this Z2. Let's take a further example. Let's consider Z3. Or in general, Zn. So what is a Zn group? So Zn group consists of n elements. So 1, e to the power of, let me call it omega. Omega, let's say, is e to the 2 pi I over n. Okay. So I just said e to the power of 2 pi I over n phase, but a particular phase, discrete phases. So I take omega, omega square, omega cube, all the way up to omega to the n minus 1. Okay. This is the set of the elements of the group, or the Zn group. And again, the composition rule is the ordinary product. So composition is just is usual multiplication between complex numbers. So if I take an arbitrary element, let's say omega to the r times omega to the s, where r and s are between 0 and n minus 1. Okay. I mean, omega to the 0 is nothing else but 1, right? Any number to the power of 0 is 1. So if I take r, omega to the r and omega to the s, where r and s are between 0 and n minus 1, okay. So this is arbitrary elements, 2 arbitrary elements, then this is nothing else but omega to the r plus s. But you see, there are two possibilities. Either r plus s is already less than, already in this range, in which case it's clearly an element here. But if r plus s is bigger than n, then use the fact that omega to the power of n is 1. Correct? Because if you raise this to the power of n, you just get e to the power of 2 pi I. But e to the 2 pi I is 1. Right? So if, for example, r plus s happen to be n plus 1, but then n plus 1 is the same as 1, because omega to the n is 1. Okay? So this way you see that immediately you get the group, this is closed, this operation is closed. Okay? Associativity is again guaranteed because the usual multiplication. And what about, let's see, yeah, so the identity element, the third point, identity element. E is nothing else but 1 again, because 1 times any number is 1, the same number, right? And the inverse, so inverse of omega to the r is the same as omega to the power of n minus r. Right? I just wrote it like this because if r is between 0 and n minus 1, well, say if r is 0, it's just identity. So it's its own inverse, right? But when r is between 1 and n minus 1, then clearly n minus r is also in the same range, right? So that is the inverse, because indeed you can multiply omega to the r times omega to the n minus r. You just get omega to the n, which is 1. Okay. So this is Zn group. And in fact, you can try to visualize what does it mean? What is it doing actually? So if after all this, on a complex plane, if I think of the complex plane, these are all complex numbers. So we can draw it in the complex plane, plot it in the complex plane, right? So the one is, of course, the real and along the real axis. There's a real axis, that's the imaginary axis. Okay, so this is the 1. And then if I draw a circle of unit length, because these are all pure faces, so their modulus is always 1, right? So they are all going to be lying on this circle. Okay? Now the first one, omega, is going to be this point here, where this angle is 2 pi divided by n, right? And so on. The next one will be, so let's take an explicit example to draw. Let's take 2 pi to the 6. Suppose n was 6. Then 2 pi to the 6 will be, well, I'm not drawing it very well. 2 pi to the 6 is 60 degrees, right? Then omega squared, so this is omega squared, which will be 120 degrees. This will be omega cubed, which will be 180, and so on, right? So there will be 6 elements, 1, 2, 3, 4. This is omega to the 4, omega to the 5. Okay. Now this has a nice property. You see, if I take this element omega and multiply any of these numbers, any of these elements, you see, rotate by, so omega times 1 is omega. Omega times omega is omega square. Omega times omega square is omega cube, right? So multiplying by omega is just rotating by 60 degrees, 2 pi by 6. Okay? So this group can be thought of, it's not the only way to think about it, but one way to think about it is a discrete rotational symmetry in a plane. Huh? It's a discrete rotational symmetry, not continuous rotational symmetry, but we are saying that whatever system I have, it's for some reason, it has 60 degree symmetry under 60 degree rotation. Okay? So this is an example. Yeah. Clearly, this is for any n. I just drew it for n equal to 3, n equal to 6. But you can, there will be more points if n is greater than 6. Right? But every time, this will be a discrete rotation. If you multiply the omega square, it's a rotation by 120 degrees, and so on. Right? So that is the other example. Now, both of these groups are pretty trivial in some sense, because both of them, this is what I said, Z2 or a generalization of that Zn. These are abelian groups, no? Because if I take omega to the r times omega to the s, that's the same as omega to the s times omega to the r. So it commutes, right? So these are examples of abelian groups. Abelian groups, or commutative groups, commuting groups. Okay. Now let's consider a slightly more complicated example, which starts, bringing up non-commuting groups, non-abelian groups. So, an example. First, before discussing that, let's consider another group, right? Which is what is called a permutation group. Permutation group. Okay. Let's suppose I have, say, n numbers, 1, 2, 3, up to n, n minus 1, n. I can consider the group of odd permutation. Suppose you had a system which had this number of things, but ordering didn't matter. If the ordering didn't matter, then there's a lot of symmetries, because you can start exchanging them, no? And say the physics doesn't depend on that. No? So in that case, in such cases, you'll have permutation group symmetry. Now, how can you think of permutation? Actually, let me again take this. First, start from a simple thing: n equal to 3, or even n equal to 2. First, let's start with n equal to 2. So I just 2 elements. Okay. Then we go to n equal to 3. First, let's go to the n equal to 2. Now, I have a permutation group where there are only 2 possibilities. One is the identity, which means I don't do anything. I just leave it as it is. Okay. Or the other possibilities, let me just call it omega. Sorry, this omega has nothing to do with that omega. I don't know, maybe I just call it G, some element G, which is not the identity. Because there's only one other element here, exchange 1, 2. So G, what it does, G takes 1, 2, 2, 2, 1. Right? It just permutes the 2 guys. But then you see, E does what? E does nothing. So 1, 2, it takes you to 1, 2. Right? E is. So now let's look at the composition rule. So I start applying successively. Okay. So G times E, will be, we're acting on 1, 2, will be, first of all, let's look at the E. When E acts on that, it gives you 1, 2 again back, but I still have to apply G on that, right? So I have to apply G on that, and that will give me 2, 1. But that's the same as the G action, which means that G times E is the same as G. And you can also convince yourself that E times G is also G. So this is the identity element. Identity element. And what about G? I mean, if I apply G times G, so first action of G takes 1, 2 to 2, 1. Then I apply one more G, 2, 1 is again exchanged to 1, 2. Which means G times G is identical. The inverse of G is G itself. But this was exactly the Z2 group, right? You see, the Z2 that we mentioned had exactly the same property, the group composition. So as a group, S2 is the same as Z2. However, things start getting interesting when n is greater than 2. So let's consider n greater than 2. So take n equal to 3. So I take n equal to 3 now. So I have the 3 elements, 1, 2, and 3. And now there are many, many elements. One is, of course, identity. I do nothing to it. Then, second, let me use the same notation which has been used here. G12. I will call G12 as the element which exchanges the first two. The first, whatever in the first positions, first 2 positions, whatever number is appearing, it exchanges them. Okay. Then similarly, I can do G23. So this exchanges the second and third position, and I can take G13. Right? G13 will exchange the first and the last position. But then you can also have a cyclic thing, right? You can have G123. It replaces one first. I don't know. That depends on your convention. So let me use a convention. This means the first guy is replaced by the second guy. Second guy is replaced by the third guy, and the third guy is replaced by the first guy. So it's kind of, I don't know whether in the notes we use the same convention, but I'm just, what I'm telling you now is that 1 is replaced by 2. So let me explicitly write 1, 2. Actually, let me just see. It is the same convention we have used here, except that I don't have the specs, so I cannot see. So this, let's just call that 2, 3, 1. So I'm just cyclically moving around. Then there's also other one, which is G132, which will, what it will do, it will replace 1 by 3. So it will replace this guy to 3, I mean this guy, 1 will be replaced by 3, third position will be replaced by 2, and 1. Okay. So these are all the elements. I have 6 elements in this group. 6 elements. So, but now it's much more complicated structure here. This is not abelian. Let's try that. Let's take G12, G23. Okay, let's take the composition of these two. Well, we act on 1, 2, 3. Well, this is the same. See what it does, G23 exchanges these two guys, right? So this is going to give me, I mean, I still have G12 applying on this. But the result of this application is 1, 3, 2. Okay. Now I apply G12. So what we said, 1, 2 means exchanging the first 2 positions. So this is going to give me 3, 1, 2. That is, by our definition, this convention, that's nothing else. So that this tells me that G12, G23 is G132 in this notation, in this convention. Now let us see the other way around. What happens? Let's first apply G12 and then apply G23. and see what happens. So this time again, 1, 2, 3. First guy exchanges these two. So I have G2, 3 and 2, 1, 3. This is the first element just exchange these two. So I got that. Now I exchange second and third. So I will get here, this will be 2, 3, 1. Right? I exchange the second and third position. But this, according to our definition here, is G1, 2, 3. So this tells me that G2, 3, 2, 3 times G1, 2 is G1, 2, 3. Okay. These are two different elements. Okay. So here we see an explicit example that this group is not commuting. Okay. And similarly, you can check also with, G1, 2, G1, 3 will not be the same as G1, 3, G1, 2, etc. So yeah, here this is what, by this conventionally, the permutation group of n elements is denoted by Sn. Okay. If I have n elements here, and the permutation group is denoted by Sn. It's a huge group. The number of elements in Sn is factorial n. Because there are factorial n ways of ordering n elements, no? So in this particular example, you have S3, factorial 3 is 6, and that is why you have 6 elements here. So it grows very rapidly. As you increase n, the number grows very rapidly, exponentially. Okay. And these are all, apart from the exception of n equal to 2, which happens to be abelian. Okay. Everything else, n greater than 2, these are all non-abelian groups. One property of this group, although this is not our main theme, actually our main emphasis will be on the continuous groups. But these are just examples, just to. But the permutation groups can always be generated. You see, here you saw that this guy, which was kind of more complicated. These were very simple elements. They just exchange two positions, right? Take any two positions, exchange. So those are like a simplest possible permutation elements, right? But the statement is that everything else can be obtained by repeated application of the simple permutations. Like as we saw, G123 and G132 could be obtained by applying these simple permutations successively. So this is a general statement that all the elements can be obtained by just taking pairs and exchanging in different orders and so on. There are also other things one can do, but grading, etc. I don't know whether I will need it. But okay. Grading in the sense that if you call this as a simple permutations, you can associate some elements would be obtained by applying. So first statement is okay. So let me just make it statement. These groups can be. So all these permutation groups can be obtained by simply starting from, so if I have n, say 1, 2, n guys, I'm looking at Sn. Okay. So in general, you can take all the elements G1, G, say I, J. So this will exchange a position I and J. Then every other element can be obtained by multiplying this in different orderings and so on and so forth. Now you can associate some grading, what's called a grading, in the sense that since every element of the group, of this Sn group, can be obtained as products of such simple elements, right? You can ask the question, do I need even number of such simple elements or odd number of such simple elements, right? So for example, here you see the G123, G132 was obtained by applying even number of the simple elements. Okay. So this I would call an even element. Okay. And similarly, this one I would call an even element. Of course, identity is always an even element because G12 times G12 is identity, right? So this also so in this particular example, these guys are odd elements, odd, and the remaining 3, G1, 3, 2, 1, 1, and 1, 3, 2. So this, and this were even elements. So the same thing you can do also for any group. Yeah.
What is the notation for the permutation if, for example, we exchange, if we permute 1 and 2 together and 3 and 4, how do we denote them?
You can, well, I mean, in that case, you can just write it as G1, 2, G3, 4.
Yeah, but there is no notation for one.
I don't know if there's any particular notation, because if I write it as G1, 2, 3, 4, that normally you would say cyclic.
Yeah.
No? So, yeah, I don't know if there's any particular notation for that.
Yeah.
I would just write it like this. Yeah, that's a good point.
I think in general it would be G21 or 3.
Yeah, even already that can generate. Yeah. I mean, even this is too much, too many. You see, you can just take the generators. These are too many of them. I mean, you don't need all of them to generate. It's enough to consider I plus 1. And you can see that everything else can be obtained by that. Because, I mean, think about it. I mean, if I want to write, let's say I want to exchange 1 with, say, some k. I want to exchange this, right? But this I can obtain by first exchanging k with k minus 1, then k minus 1 with k minus 2, k minus 2 with, and successively, right? So this element, G1k, I can write it as G12 times G23 times etc. Gk minus 1k. So you can do that. All right. So now, okay. As I said, I will not be needing these things. There are some examples. Now let's go to some simple continuous groups. Of course, the very known example is, of course, the set. I mean, still I'm talking about discrete groups, but now I talk about infinite discrete groups. Infinite discrete groups. Okay. For example, take the set of all integers. So this is the set of all integers. And consider the operation O to be simply addition. Is the simple addition, the usual addition of numbers. Okay. Well, it's clear. I mean, if I take some integer n and m belonging to the integers, then n plus n is also belonging to the integer, right? Sum of two integers is an integer. The identity is associative by definition because usual addition is associative. If I to add three numbers, it doesn't matter whether I first add the first two numbers, then add the third, or first I add second two numbers and then the third, first one. For the identity element is simply 0, because 0 plus any number is the same number, right? So the identity element is a 0. 0. And the inverse of n is equal to minus n, because n minus n is identity. So this is an example. So it's an infinite group because there are an infinite number of elements, right? And the usual addition. Okay. However, you cannot use the usual multiplication as an operation. Okay. Because if you were to use usual multiplication, then there will be a problem. Because so what will be the inverse of an n? Inverse of n will be 1 over n. Because identity will be 1, right? If I take the multiplication, identity will be 1. Because 1 times any number is itself, no? So 1 will be the identity. But then if I give you an n, I ask you what is the inverse, it will be 1 divided by n. But 1 divided by n is not an integer in general, no? So that will not be, usual multiplication will not be this will not be a group. Integer will not be a group. Of course, you could also replace this set of integers by a set of all real numbers. Right? This now, the set of all real numbers This is again infinite, but it's uncountable. Right? This is infinite number of elements, but it's a countable. Countable, you know the concept of countable. You can count them, 1, 2, 3, 4, all the way to infinity. When you talk about the real number, it's not even countable. Okay? So this is like is an infinite, but uncountably infinite. Uncountable. Infinite set. And just take the usual addition. The operation is simply the usual addition. Usual addition. And this is again clear because if I take number x and y, x plus y is again real number. So real number, set of all real numbers is called R. Okay. Again, identity is 0. Is 0. And the inverse of x is minus x. That's fine. Again, multiplication is not a well-defined group because the inverse of 0 doesn't exist, right? Okay, inverse of 0 is infinite. Yeah, so it's... I mean, you can make it into a group by removing the 0. Okay. So all the non-zero numbers, and then you can define the multiplication. But if you take all the real numbers, that's not, because 0 is included there. These groups are again quite important because this group is nothing else but in terms of physics, you would say it's a translational symmetry in one direction, right? Because you know the symmetry is like the translation by x by if I take an element x here, the group that we are thinking about is a translation by x, right? So that's an example of a translational symmetry. That appears in physics via translational symmetry. Or if you talk about these infinite discrete groups, that can appear in the crystallographic situations. No, you have a discrete translational symmetry. Okay. Right. I think the other example is again the other continuous group example. These are called continuous groups because you see there is the elements which exist here, x, this is continuous variable, right? You can make infinitesimal transformation, change from x. This is not the case with this. Here, these are an example of continuous groups. The same thing you can do for the example I mentioned, which was the Zn group, right? The Zn group was Zn was basically 1 omega to the n minus 1, where omega was e to the power of 2 pi I over n. And it had the meaning, what it had the meaning of rotation by rotational thing where this angle is 2 pi by n, right? That was it. But again, you can talk about, so this will be an example of appearing in physics where somehow there is a symmetry which is not a continuous rotational symmetry, but there is a discrete rotational symmetry, right? But you can also talk about continuous symmetries, right? So you can take the continuous symmetry, which is again the rotation. So let's just take rotation here, rotational symmetry. Let's take a two-dimensional plane. And rotate, so I have a, let me call it x and y axis, okay? And I can rotate by theta, some angle theta, okay? Then when I take some element, then x, y will go to some elements x prime and y prime. So some point here x, y, I rotate this point by an angle theta. Okay. So this point I call it x prime and y prime. Okay, some new point. Right? Then you know that x prime y prime is just simply cosine theta x plus, so cosine theta, sine theta, minus sine theta, cosine theta, right? XY. Okay, maybe this is plus and that's minus, I'm not sure. I think, yeah, because you see the x prime is becoming less than x, no? So this should be minus and that's plus. I'm not sure, that you can work out. It is a question of whether you're going counterclockwise or clockwise. So it's something like this. Yeah? This is the rotation group. And so this, again, you can see, so here I have written it as a matrix. But you can also do it in another way. After all, this two-dimensional plane, I can think of it as a complex plane, right? Z. So any point will be given by its radial, I mean, any point will be labeled by, labeled by Z, coordinatized by Z. Z, this radial distance is simply the modulus of Z, okay? And this angle is some e to the power of I theta, e to the I phi. Now I rotate this point by theta, what is going to happen? Modulus will not change, right? But phi will become phi plus theta. Okay? So basically, if I write Z, which is nothing else but r times e to the I theta, where r is the radial length, radial distance from the origin. Okay. Sorry, I use the theta here, so let me call it phi here. And then I rotate, I make this rotation, and then I rotate by theta. What's going to happen? Z will go to Z times e to the I theta, which is the same as r e to the I phi plus theta. So it does nothing, but it just shifts phi by theta. Okay. So this is even easier way to look at it. So all one is doing is I have a circle. Phi is a continuous variable because, this phi is arbitrary, right? Because Z could be anywhere. So phi is anywhere between 0 and 2 pi. 2 pi is itself, 2 pi is the same as 0, right? Because it's a circle. 0 and you keep increasing, when you arrive at 2 pi, you come back to itself. No? And theta is just doing nothing but just rotating the circle, right? By a continuous amount. Theta is arbitrary. No? So this is the generalization of what I call Zn, no? Where Zn was discrete rotation, but now it's a continuous rotation. So the g theta, so g, I will denote the element by g theta. It takes phi to phi plus theta. Then you can take the products, the products of these elements. So g theta with g theta prime will take this phi to phi plus theta prime, right? And in this case, ordering doesn't matter. So it's again example of abelian group. So this rotation in two-dimensional plane, this is a abelian group. So these are examples of continuous groups. Yeah, this is a good example to see. You see, in this picture, once you think of a complex number, and in terms of the phase, this operation is very simple operation, right? With just phi shifted by phi plus theta. No? But here in this language, it's not so obvious. But please try to do that. Probably many of you have done it. But try to check this. That so g theta takes xy to cos theta. Say I don't know. This I'm not sure. Please check also whether this plus minus in that convention. If I'm thinking of counterclockwise rotation. Yes. Okay. Or this is for the clockwise. Okay. Yes. Okay. So counterclockwise and plus minus. Yes? So so cos theta minus sine theta, cos theta, okay. And g theta prime will be the same with the theta replaced by theta prime. Then check that thing that if I apply g theta prime, if I look at the composition g theta prime times g theta, you will indeed get the similar matrix. Take the product of these two matrices, then you will find exactly the same form of matrix, except theta is replaced by theta plus theta prime. Okay? So please check that, because that will also, I'm sure you have all done the matrix algebra, but do some more if you practice a bit more, it will be useful, please. Because in this course, there will be a lot of matrices floating around. Okay. So now, I think I have basically finished the first chapter. Yeah. I will, there is in the last part there is a discussion about the representation, but I will skip that and go, because representation will be talking in detail later on. Okay? So I will just skip that and move on to, yeah, actually it's given here. But any questions right now? Any questions on that? Any questions, I mean, about these things or in general? Yeah.
Just have remark that in the beginning, the notation for a general group, the elements was indexed by the integers.
Yeah,
which indicates
that is basically a finite, I mean, or countability theory, yeah. But in general, that is not true. Yeah, I mean, yeah, correct.
The existence of the inverse, there is a unique inverse for.
There's a unique inverse, yeah.
That's a request, or
That's a requirement, yeah. There's a
requirement.
unique inverse, and in fact, both ways. I mean, G times G inverse is the same as G inverse times G. So even though the group may be non-abelian, but for these two elements, it should be the same. I mean, ordering shouldn't matter. And there's a unique.
It's unique.
That's true.
But I think it is not required. From this definition, we can prove that.
Yeah, you can prove by
Yeah, more or less you can prove, yeah. I mean, with some assumptions, I think you can prove, yeah, correct. Yeah. With some assumptions you can prove, yeah. Okay, so now let's continue, since I already was talking about these rotations. Yeah, so let's go back to this this part here. So the next chapter, actually, we are starting from here. I mean, of course, yeah. You see, we said that this rotation group, what it does, it leaves something invariant, okay? That is the distance, radial length, right? It means that the x squared plus y squared, which is the r squared, this is invariant, under such a rotation, under g theta. Is it? So one can ask, I mean, what can I kind of, okay, I have, once you see this explicitly, I have written down the matrix, you can of course check that, I mean, this cos theta plus x minus sin theta y plus, I mean, and these transformations, and I just plug that, okay, let's just do that. So x prime square, so we have x prime square plus y prime square, but that's the same as cos theta x minus sin theta y square plus sin theta x plus cos theta y square, right? So let's just open it up. So this is x prime square plus y prime square, right? Let's open it up. So let's first look at the x square terms. So x square term gets a cos square theta from here and a sin square theta from there. And cos square theta plus sin square theta is 1. So that is 1. Similarly, let's look at the y square term. Once again, I have a minus sin theta square, but minus square is 1. So sin theta square plus cos square theta, that's also 1. So you will get x square plus y square. And the cross terms cancel, because of relative sign, right? So indeed, you see that x prime square plus y prime square is x square plus y square. Now this you can try to rewrite it in a slightly different way, which is more suggestive, right? After all, x square plus y square, I can write in the matrix notation, x, y, and x, y. Right? This is a 2-column vector, that is a 2 That is, these are just two, I mean, a row is a row vector, okay, with the two columns. Here is a column vector with two rows. And I just use the usual matrix multiplication. If I just multiply this matrix out, so this is, you see, this is 1 cross 2 matrix, right? This is 2 cross 1 matrix. I can multiply such matrices, and the resulting matrix will be 1 cross 1, which means a number, right? And indeed, you multiply that, it's simply x squared plus y squared. So this length square, I can write it as this matrix, I mean the transpose of this matrix times the matrix. I mean this matrix is a column vector. So transpose of the column vector times the column vector. That's the length square. But in this way, in this language, I can understand this criterion, and I can, write it more conveniently. What is the most general transformation which has this property that the length square does not change? Okay? What is the most general, linear transformation? Okay? So I want to consider the most general transformation where xy goes to x prime y prime, but I want to consider linear transformations. Okay? So in other words, this must be any linear transformation. I can always write it as a matrix multiplying the original guy, right? Yeah. I mean linear transformations. Well, what does it mean, linear transformations? I mean, let me just use that notation, capital X. When I say capital X, I mean this column vector. Okay? So if I am given capital X and capital Y, capital X and capital X and capital Y, and I take any linear combination of this guy, okay, where A and B are some numbers, okay, then the transformation property is such that the whatever the transformation is, how shall I call it? G is this group element, I mean some transformation element. So G acting on A of X plus BY is the same as A G of X plus B G of Y. This is a linear. It's a linear, you see. Okay, it's a linear map. I mean pictorially, pictorially what I mean is that if x goes to some point, x goes to x prime and y goes to y prime, then ax plus by goes to ax prime plus by prime. Okay? That is the, so they are called linear transformations. And such linear transformations can always be expressed in terms of in the matrix language. So therefore, this I can always write it as some matrix acting on x. X being this column vector. This matrix multiplication is always linear, right? I mean, it satisfies this property. If so, then I want to ask, what is the condition on M? I mean, so M is some matrix, 2 by 2 matrix. M is this is a 2 by 2 matrix. So the question is, what is the condition? What is the condition on M such that the length square, the length of the vector, or length or same as length square of the vector of x is unchanged? In other words, x prime square, which means x prime square, the length square, is the same as x length square. Okay, this I call x prime. Well, so that you can write it in the following way, in the matrix notation. Length square, x length square is nothing else, as we saw, is simply x transpose x. Okay? So similarly, x prime square is nothing else but x prime transpose x prime. Right? Remember, these are all 1 cross 2 matrix. It's a row vector. That's a column vector. So there's multiplication. Okay. So, but now we are saying x prime is m times x. That's for some matrix n. Then what is this guy? This guy is nothing else. I take the transpose of that, but then I take the transpose of order changes. So you get here x transpose, m transpose, m, x.
So it should be okay.
Right? So the condition that these two are the same implies that this guy is equal to identity matrix. So the most general condition on M is that it should satisfy this condition. Any M which satisfies this condition will preserve the length. Right? Such matrices which satisfy this property are called orthogonal matrices. Okay. I mean, this is a general definition. Here I was talking about 2 cross 2 matrices, but this is also true for n by n matrices. If M was an n by n matrix, or an arbitrary square matrix, and it satisfies a property that M transpose times M is equal to the identity matrix, then that matrix is called an orthogonal matrix. And it is the importance of this matrix is precisely, this orthogonal matrix is precisely that the length square is invariant. If you apply the orthogonal matrix on some vector, then its length doesn't change. This is the point. So then you can, let's again go back to the 2 by 2 case. So what is the most general matrix that you can write down, which is orthogonal? Okay. This is of course, actually the most general matrices, you can write it as this, sine theta, cosine theta. Okay. But it's not entirely that. There's only basically one more element. Okay. You see what this does. This rotates, right? As we saw already, this takes a vector and rotates by an angle theta. And of course, under rotation doesn't change. Right? I mean, the length doesn't change. But there is one more thing, which is what is called the parity transformation. It's a discrete transformation, parity transformation, which just changes one of the coordinates to minus. Okay? You see, that cannot be obtained as a rotation, right? Because if I rotate by pi, this will go there, okay? But this will also go there, right? Or if I rotate by pi by 2, this will go there, but that will go there, right? But what I mean here is that just a parity. Don't do anything to this, just reflect. Okay? So we are saying xy goes to minus x, y. This is not a rotation. Okay? So the matrix, if I want to write it again in terms of this matrix, this is nothing else but minus 1, 0, 0, 1, and xy. This rotation matrix, the determinant of this matrix is minus 1. Right? But if you look at this matrix, the rotation matrix, if you take determinant, it's this times that minus this times that, right? So which is cos squared theta plus sine squared theta, which is 1. So all the rotation matrices satisfy this property. The determinant is 1. But the parity is not. Parity is determinant minus 1. Right? In fact, you can see if there's a matrix which satisfies this condition, M transpose M equal to identity, I don't know what shall I call it. This identity is the matrix identity, n by n or 2 by 2 matrix identity. Then if I take the determinant of both sides, then if I compute determinant of this matrix, both sides, here is determinant of 1, but determinant of 1 is simply 1, right? The one just diagonal, just everything is 1, 1, 1, so multiply this as 1. But determinant of product of two matrices, square matrices, is the product of the determinant of the matrices, right? So this guy is nothing else but determinant of M, sometimes I use capitals sometimes, determinant of M transpose times determinant of M, right? But determinant of a transpose of a matrix is the same as the determinant of the original matrix, right? So this is the same as determinant of M squared. Correct. So what we are saying, determinant of m square is 1. Okay? Determinant of m is a real number. Actually, determinant of m square is 1. This implies that determinant of m, it can be either +1 or -1. Two possibilities. That's all. There are only two possibilities. And we found here, this is the one with determinant 1, +1, and this guy is the determinant -1. And of course, you generate the full group by multiplying also these elements. Okay. So this group is called O2. The notation. O for orthogonal, 2 because we're talking about 2 by 2 matrices. In general, if I talk about an n by n matrix and impose the condition that it's orthogonal, then it's called an ON group. Now let us generally see that, let's see if this forms a group in general, ON groups. Okay, so we have O2 in mind, but let's just do it generally, ON. So I look at the ON group, which means it's a n cross n orthogonal matrices. With all the entries are real. I'm considering here real. These are all real numbers. The entries of the matrix are real. Later on we'll go to complex cases, but for the moment let's stick to the real. So let's suppose I have G is an ON, G and G1 and G2. Just here I'm not enumerating the group elements, just two elements whom I'm just calling G1 and G2. G1 and G2 belong to ON. So the question we are asking is, if I take so we want to show that there is a group with where the composition rule is the usual matrix multiplication. Matrix multiplication. So I'm just using the usual matrix multiplication as a composition rule. It's all natural. It's obviously associative. Matrix multiplications are associative. Okay? So that part is fine. Now, so let's say G1 is an element of ON, which means that implies that G1 transpose is one identity. Okay? And similarly, G2 transpose G2 is also identity. But now we want to check, because the composition rule was simply ordinary multiplication. So the question mark is G1, G2, does it belong to ON? That is the question mark. It is certainly an n by n matrix, right? The question is it orthogonal? Okay, that's the question. So let's just check that. So we want to look at G1 times G2. I'm not putting here this thing because this is ordinary matrix multiplication. And then I take the transpose of that, but when I take the transpose, the order changes. Okay? So this becomes G2 transpose, G1 transpose. Okay? Now I open it up. I mean, this is associative, so it doesn't matter how I output them. First I multiply this, G1 transpose G1, but that is because G1 and G2 satisfy that. This is identity. Okay? But identity, of course, commutes everything. I can move it across. Then I'm left with G2 transpose G2, which is also identity. So this is indeed identity. So this shows that this forms a group, right? Not exactly. You still have to check. What is the identity element? Identity element is simply identity. Identity as a matrix, n by n matrix. Okay. This is obviously orthogonal because transpose of identity is again identity, and that times identity is again identity. Inverse of group of element G is just the standard G inverse, where G inverse is in the matrix sense, in ordinary matrix sense. But we need to check something, whether this is also orthogonal, right? That's all we need to check. Certainly, this G, since the determinant is not equal to 0, right? We already said this implies the determinant of G1 is plus or minus 1, right? So which means it's not 0, right? And you know that inverse of a matrix always exists if the determinant is not equal to 0, right? So G inverse, so let me just say, this exists since determinant of G is not equal to 0. In fact, it is plus or minus 1. So this certainly exists as a matrix. So it is certainly a matrix. The next thing that we need to check is that this is orthogonal. But that's, again, is just a basic property of this here. So I want to check. So the question is, G inverse, is a G inverse transpose G inverse identity? So there's a question mark here. But that's immediate because I mean, this is nothing else but G transpose inverse. Okay? So then I have a G inverse. And then I use the fact that this is the same. This is the same as G transpose inverse. Okay? And G transpose is 1. Okay? So therefore, this is. So which means that this is also orthogonal. So therefore, orthogonal, the set of all orthogonal matrices forms a group under usual matrix multiplication. Yeah. So, I mean, going back to O2, O2 you can always think in terms of rotation and a parity. You put together a parity and rotation and form a bigger group. By the way, the rotational group, just the rotational group, remember has determinant 1, plus 1. Those are called special orthogonal groups. So here I said that O2 or ON in general, or let's focus on O2. So O2, you had two possibilities. Determinant is equal to plus 1 or minus 1. The rotation part of it satisfied this. So this was the rotation part. Okay? There is a theta angle, cos theta, sin theta, that matrix. That satisfied the plus 1. And this minus 1 was basically parity, which is generated by parity. Then of course you can multiply these guys. No? I mean, you can have a cos theta minus sin theta, cos theta, and multiply to this element, which we said is minus 1, 0, 0, 1. This is clearly, since the composition, the product must be again an element of O2, right? But then when you do this, you will find that this is multiplying this the upper. So this becomes minus cos theta, sin theta, cos theta. And this now determinant is minus 1. So this is not a pure rotation. It is a rotation together with a parity. But if you want to restrict yourself to pure rotation, okay, then you impose a further condition. You say, no, I'm not going to consider all the orthogonal groups, but I'm going to consider only those elements whose determinant is plus 1. Okay? And that restriction you can put, because if I put that restriction, the determinant is plus 1, then the product of two such matrices will again have a determinant plus 1. It will not become determinant minus 1, right? Right? If I take G1 and G2, which are in O2 or ON, but with determinant plus 1, the determinant equal to plus 1 for each of them. Then if I take G1 times G2, this will be again an element of ON, because ON is a group, but moreover, the determinant of this guy is plus 1, because determinant is product of the determinants. Each of them is plus 1 times plus 1 is 1. Okay. So if you putting this extra restriction gives you a subgroup of the original group, a subgroup. And that group is denoted by SON. When you put this further restriction, it is SON.
This is always the case with ON groups, that we have only rotations and reflections.
And reflections, yeah.
Are they the only ones that we can generate of other matrices?
Yes. I mean, you can have reflections in different directions. You're in many planes now. You can start rotating different planes.
But they're always rotations or reflections or combinations of
Yes.
samples. Can one prove that?
Yeah, I think one can prove. Okay, maybe when we come back to some more complicated examples, we'll come to that. Yeah. So, right now, much time? So this was kind of you see this group, SO group, or even SO group was basically SO2 group was basically labeled by one parameter theta. Okay, so it's only one parameter. Of course, if you go to SON, there are many more parameters because you have n-dimensional space and you can have rotation in different planes. You can choose each two plane and you have a lot of rotations. No, so there are many parameters. Already in 3 dimension, you remember when you discussed the rotations in 3 dimension, there were these Euler angles, right? So there were 3 parameters there. So as you go to higher and higher n, it becomes more and more. Number of parameters becomes more and more. Actually, yeah.
What's the relation between the number of the parameters and the number of the dimensions of the space?
Yeah, it's basically n squared minus 1. No, sorry, n times n minus 1 by 2. N times n minus 1 by 2. This is the number of parameters in n-dimensional rotation group. N times n minus 1 by 2. So indeed for n equal to 2, you get 1. N equal to 3, you get 3, and so on. That is right. I mean, one can count, let's see, just by trying to look at these conditions, that if I have an n by n matrix, M, which satisfies this n by n matrix, which satisfies the condition M transpose M is 1. Okay. And the further condition, the determinant of M is 1. With these conditions, then you ask, well, I mean, so you see there will be lots of conditions will appear. And then you see how many parameters are left over. I mean, maybe just to give you an idea. So if I only look at, it will turn out that when we discuss, I mean, to count these dimensions, it is more convenient to look at infinitesimal transformations. Then you can count very quickly. But you can also count this here, although it's slightly more complicated. But you ask the way you ask the question is the following. I have M, I mean, if I look at M, n by n matrix, first of all, how many parameters are there? N squared. The real parameters. So there are n squared parameters, right? There are n square entries. Each place you need to put some entry, n square parameters. But now you have this condition, M transpose M equal to 1. Okay. How many independent conditions are there? That's the question, right? Now notice that M transpose M is a symmetric matrix. Correct? Symmetric matrix, because if I take the transpose of this, I will get back the same. If I take the transpose, M transpose M transpose, then when I take the transpose, I have to change the order. You will get here transpose of this times the transpose of that. But TT, 2 transposes gives you back original matrix. So, and this transpose of this matrix is itself. So it is a symmetric matrix, right? So how many conditions will there be? A symmetric matrix means what? I mean, I have the entries in the diagonal. Then I have some entries here. But these entries are not independent. These entries are the same as that entries, right? So these conditions, this is a matrix equation, right? This is an n by n matrix, that's an n by n matrix, right? So I have to, each component I have to say that they are equal. So to begin with, it looks like there are n square conditions, right? But actually not, because the left-hand side is symmetric. So whatever you get here is the same there. So you don't get new conditions, right? So what is the number of conditions? It is the diagonal ones, which is n, and the off-diagonal guy, which is half n minus 1. Correct? So number of conditions is equal to n, coming from the diagonal guys, right? And half plus half n times n minus 1. These are the total number of conditions. On n square variables, I have n square variables altogether. So you see total number of conditions here, this is the same as half n times n plus 1, right? These conditions. So from this n square parameters, these conditions will fix so many of them, right? Then what is left over? It is this minus that, right? Those parameters are left over. I mean, they are not fixed by these conditions. So it's just a difference between this and that. So n squared minus 1/2 n plus 1 is nothing else but half n minus 1.
But determinant put another condition.
Determinant doesn't, because because you see, once it is orthogonal, determinant can only be plus 1 or minus 1. So there's no continuous parameter linking them. For the unitary groups, it will be, right? But here, this condition already implies determinant is either plus or minus 1. So there's no continuous parameter which can take you from plus 1 to minus 1, right? So yeah, that doesn't give any extra condition. That is right. That's a problem. But we will discuss later on. In fact, actually the whole course will be really discussing the infinitesimal generators. This is called a Lie algebra. So yeah, once you look at the algebra, it becomes much easier to count, because the conditions are linear conditions. You see, these conditions are nonlinear conditions, right? M transpose times M. So it's quadratic in the parameters, right? If you write M, the matrix M with some parameters, x1, x2, x3, all the way xn square parameters, right? Then when I take the product, I'm going to get quadratic equations in the unknown variables, x1, x2, etc. No? Whereas once you go to the infinitesimal transformations, you'll get linear equations. It's much easier to analyze them. Okay, maybe I should now stop. I think so. Tomorrow I will continue with this. Towards the end, what I was mentioning towards the end was that here in the O2 example we discussed, there was only rotation part was just governed by one angle theta, right? But theta and theta plus 2 pi is the same, right? Whether you rotate by theta or rotate by 2 pi plus theta, it is nothing. There's no difference. So these are examples of compact groups. These are called compact groups. The range of parameters is a finite range. Yeah? Okay. Or let's say the volume of the group is finite. The volume is simply the integral of the d theta, which is 2 pi. Okay. This is a compact group. But what we are studying here in the RQM, relativistic quantum mechanics, there you have Lorentz groups. Okay. Lorentz groups are not compact. Okay. Because the boost you can do by any amount. No? The rotation part is still the same, but the boost part that makes it non-compact. Right? So I will just discuss that as an example. Just already in 2 dimension. In 2 dimensional, one is like time, other is space. To show the crucial difference between the two groups. And then go on. Yeah. Okay. All right. So any questions? Please, feel free to ask questions. By the way, you'll have a tutorial, not this week, because I think it's the first week, so you still won't have enough homeworks or not enough time to do homeworks and so on. But next week there will be a tutorial. There's one of the postdocs here, Arnab Rudra, doing the tutoring. So you should feel free to ask questions, and in fact you should ask questions. Don't hesitate at all. And my office is 279. My office number is 279. Is 279. Okay. So if you have some questions, just try. You can just come. If I am busy, I'll just tell you, okay, come at such and such time. Okay. Who's studying this Fujikawa method? Wow. No, this is leftover from the diploma thesis defense. I should stop this. Stop here, right?